So I am Brian Lacki. I'm a theorist associated with Breakthrough Listen. And in this talk, I'm going to present some results, or some ideas I've had from a couple of different projects I've done over the years. They seem very disparate, but they do have an underlying theme under them, which is really to this question of, can you have a technosignature that really outlasts its progenitor ETI? And I'll close with a bit of a hint to the future and to the next talk by Lewis. So I think most of us are familiar with the Drake equation. It's very common. One criticism of the Drake equation has been that a lot of these factors, the prevalence of life, the prevalence of intelligence, how often it communicates, most of these factors aren't really well known. So the Drake equation sort of has been criticized as being, in that sense, vacuous, because how can we predict what n is if we don't know what these other factors are? But I do think the Drake equation, regardless of that uncertainty, it does encapsulate a certain fundamental issue with SETI, which is that people tend to emphasize how far away ETIs are, but it's not just a separation in space, it's a separation in time. And that comes in with this lifetime factor, L. So we had that talk by Michael Garrett yesterday, where he suggested that the lifetime that ETIs are communicative might be very short, of the order of years or maybe decades. But if you compare that to the lifetime of these host stars, so this is sort of a chart I made for one of the Breakthrough Discusses, where the question came up of, could we do SETI with Alpha Centauri? And one sort of issue you run into is that if you imagine that there's just one ETI arising per star, which is the usual optimistic estimate, the odds that we happen to overlap where those ETIs exist in geological history are almost zero, unless these things can last for geological times. If you just pick something from the solar lifespan at random, the odds that you even land between the Cambrian explosion and right now is only of order like 5%. So you can imagine that even if these ETIs last for thousands and thousands of years, most times when you're looking at a star, you're not seeing anything. So the question becomes, well, how do you bridge time? One thing to keep in mind is that the technosignatures we detect, they may not be a representative sample, an unbiased sample of all the technosignatures that exist. So one way to think of it is that longer-lived technosignatures, they sort of reach further into time. And as they reach further into time, they're more likely to reach whatever window of time you're looking at. Another way to think of it is that you have this sort of a haystack, this higher dimensional space. And for objects or technosignatures that live longer, you're sort of reaching further back into the haystack because those are the ones that can survive to reach your window. And you can sort of formalize this and calculate how long the expected technosignature, sort of the expected lifespan of a technosignature is just from the way you're sampling it. And that depends, it turns out to be fairly heavily dependent on the tail of the distribution. You're very sensitive to things that live very long, even if the mean lifetime is relatively short. So what sort of things might last that long? Well, one thing so we do know of a complex system that has survived over geological times, and that's the Earth's biosphere. It's been going for 3 to 4 billion years. This image you see here on the left, that's a stromatolite colony in Australia, and we have fossils of stromatolites from at least 2 billion years ago. And the way that these things manage to sort of bridge that distance in time is through replication. The individual organisms, they don't last long, but by creating copies of themselves, the community as a whole persists, at least in the form of a biosphere. And ETIs are unlike most astrophysical phenomena in that they can potentially replicate. And the way they would do this is through interstellar travel. An ETI society on one world might be vulnerable to nuclear war or ecological collapse. But the idea that has been thrown around is that maybe you could establish another location. You could maybe establish several more locations, and they can sort of reinforce each other. Another thing they can do is that they can, if you sort of jump from star to star, you might set off this wave of settlement that spreads across the galaxy. And whenever one world falls, there's sort of another descendant, something to take its place, sort of like on the Earth's biosphere. I think this, if this kind of thing can happen, it's very profound because nothing else in astronomy that we know of does anything like this. One consequence is that by increasing the number of ETIs that are out there, you can increase this well past even the sort of optimistic estimate of the Drake equation. Rather than n being equal to L, it could be equal to the number of stars in the galaxy. And one advantage of that is that it makes it more likely that whatever weird technosignature you're imagining, or even things that seem obvious to us, but that may not be obvious to ETIs. Maybe most ETIs don't do narrowband radio signatures or radio beacons, but maybe a couple do. And if you have an entire galaxy of ETIs broadcasting, that becomes more likely. But this idea is kind of controversial, and there are various people who argue against this. It leads to the Fermi paradox. Why haven't they done this? So apparently, for some reason, either this has been done. If you do have this sort of galactic settlement, this even a galactic ecology, I would think of it, it's not very visible. And so maybe it's too subtle to see. But another possibility is that either it doesn't occur, or there is some kind of unprecedented galactic scale disaster, some kind of mass extinction. So without that, then you're just sort of left with these isolated ETIs that sort of pop into existence, and then they live for some time, perhaps, or before they either die or move out of detectability because they move on, like in Michael Garrett's talk. And so could they leave anything behind that could sort of announce that they've been here, even in their home system, that we could see from an interstellar distance, even after thousands, millions, or even billions of years? So this idea of a passive technosignature that you could see without any sort of power, any sort of maintenance. This is actually pretty well known in SETI. There's been one example that's been formed its own little subfield of SETI, which is the anomalous transits. The idea was proposed about 21 years ago by Arnold, and the idea is that we see planetary transits. But most planets are round, basically. They might have rings or something, or moons, but there are no square planets. If there were, that would be, if there were and they were natural, that would be as exciting a discovery as ETIs themselves. So by looking at the transit light curve, you could potentially see these anomalously shaped transitors, these anomalously shaped occulters, and that could serve as a technosignature. And the key to this, the reason it works is because it's sort of using the star itself as its power source. It doesn't need any power of its own. It's just the star itself is providing that power, and all it has to do is block it out for a certain time. So one question is this the only kind of thing like that? So within our own solar system, you can sort of see in one of my works, I considered sort of the opposite of this, which is specular reflection. We, of course, see satellites in orbit all the time. Sometimes these are just diffuse reflections, but there are many natural objects that diffusely reflect light within our solar system, asteroids, meteoroids, maybe comets, although those would be visible by their tail and so on. What is generally unambiguous, however, is that a lot of these satellites, they have specular reflections. They have basically mirror surfaces. And the mirrors, when the angle is just right, they reflect the sun directly to you. And so the surface brightness of the mirror, it goes basically as surface brightness of the mirror is similar to the surface brightness of the sun. So it becomes a lot brighter than you expect from a diffusely reflecting object. So even in the 90s, you could see these iridium flares. These were a spectacular technosignature, reaching visual magnitudes of around -6, -7. So these satellite glints, they're a common background for optical transient searches. So we know that these are a possible technosignature. So how might you use mirrors as a technosignature distinguished from that from our own technosignatures? Well, the thing is that Earth satellites are orbiting the Earth. But we don't have a lot of satellites out in the interplanetary space, not enough to really get high event rates for these things. So the thing is that the mirror, it reflects sort of you see that specular reflection basically in a cone that has a similar opening angle to the angular width of the sun. So that would be about half a degree for a mirror at 1 AU. And for something in low Earth orbit, it's going to be within that half a degree just for a few seconds. But in interplanetary space, these mirror glints, you would see these flares that last for several hours. So this is unlike the kinds of satellites that we see. So this would indicate that there's something out in the asteroid belt or whatever, and we don't really expect many mirrors out in the asteroid belt. And you can sort of calculate how visible this would be. It really depends on how fast the things are spinning. That spinning makes it so that rotation makes it so that you're more likely to see something because it's sweeping out a whole region. But on the other hand, you only see it for a fraction of the time. So overall, what you find is that you could probably detect these things if they're not really spinning at a distance of 1 AU if they're a fraction of a square meter. If they're spinning really quickly, you might need more like 10 square meters, 100 square meters. So this is within the solar system. The question then becomes, well, can you apply this out to different solar systems? Could we use a mirror as a signal lamp? And I would argue that, in fact, the advantage of that for like a sun-like star is actually no greater than that of an occulter. And the reason is that basically mirrors preserve surface brightness. It's a fundamental thermodynamic constraint, basically. The specular reflection, it only increases in both cases, the amount that the brightness of the star deviates is the same. It's just that in one case you're sort of losing. In one case you have a dip in the brightness of the star, and the other it's a bump. But one thing you could imagine is that if you had a source that was really, really small and a lens that was really big, as that lens moved in front of that very small source, well, most of the time it's just sort of magnifying empty space, and you get this sort of occulting transit effect. But if everything aligns just right, the lens, when it passes over that very small source, it lights up with that same surface brightness, so it becomes a whole lot brighter. And so I call this lens flare. But you need something that's very small, very bright, something very hot, basically. And the hottest thermal sources that exist in the universe, they're low mass X-ray binaries, in particular ones with neutron stars, which have a boundary layer. So you have this matter that's sort of orbiting and it's falling into the neutron star at a good fraction of the speed of light. And then within basically just a couple of square kilometers, it's being brought to a stop. So that releases a tremendous amount of energy. So these things can be extremely bright. So the idea is that you might have an X-ray lens passing in front of one of these. If you do just sort of order of magnitude estimates, you can imagine that these things might be visible from other galaxies. And so you just need a lens passing in front of it. It doesn't need to have any power, and you can create these signal flares that are visible across the galaxy, even from across the local group. When you do the actual estimates, part of the issue is that you don't know where they're occurring. These transits would still be very rare. The other issue is that actual X-ray optics, they're not achromatic lenses. The kinds of things that we know of, they would have severe chromatic aberration that significantly reduces the fraction of the spectrum that you're magnifying, and that greatly reduces the number of photons that you get. But there's another sort of a passive occulter that you might see from a large distance, which is a Dyson swarm. These things sort of absorb most of the starlight from their host star, and then they irradiate that in the infrared. You might be able to see that infrared distance, that sort of infrared waste heat across kiloparsecs with current surveys. And so now you're imagining these things are as big as a solar system. And surely something that big, surely that would be immortal and also easy to detect. Well, people have certainly considered the easier to detect part, but are these Dyson spheres really immortal? That's sort of been one of my latest works. Basically, you have a literally astronomical number of swarm elements, whatever these things are made of. And if you imagine that they're put on random orbits, they crash into each other. We see this process in debris disks around other stars. We see this when once in a while you see asteroids colliding within our own solar system. And it's unfortunately becoming a problem with our own satellite system, artificial satellites, where satellites collide with each other or even with just debris. And that produces a huge amount of fragments, each of which is moving at hypervelocity and can be a severe issue. So this collisional cascade thing, if you assume that everything is on a random orbit, the collisional cascade time is basically proportional to the covering factor times the orbital, or it's really inversely proportional to the covering factor, but otherwise it's roughly the orbital time, which is very short for something like a Dyson swarm. You can imagine putting these things on more organized orbits, but eventually, once you get a certain amount of randomness, and if these things are on a Keplerian orbits, at least supported mostly by gravity, you get this really fast collisional cascade. Now you might imagine that these occulter swarms, these occulters like the Arnold 2005 proposal, or even these systems of lenses, they might be safe. You don't have a whole system of them surrounding a host star. The issue is that in order to really see these occultations, you need enough to cover every possible inclination if you're using this as some kind of beacon. So for occulter swarm, you typically need several hundred of these planet-sized occulters. And so these are different inclinations. And one thing you run into is that most star systems, they have planets or they have companion stars. So what you find is that these companions, they induce gravitational perturbations in these swarm elements. And over a process of a few thousand to a few million years, the things at high orbital inclination, they become eccentric and they start crashing into each other. So by this Kozai effect, you might imagine additional instabilities related from radiation pressure and so on. So now if these things are being maintained, they can course correct. This may not be an issue, but if the ETIs vanish for some reason, these things might survive for quite a while, but we're talking more like thousands of years instead of billions.
2 minutes.
Okay. So part of that's going to bias which ones you see, and part of the issue is that the orbital period is so short. What happens is that these things, when they collide, each fragment produces more fragments, and the entire swarm gets destroyed and it gets ground to dust, as I say. Eventually, when that dust reaches 0.1 to 1 microns or so, depending on the host star size, that material gets blown out of the home system. So I'm just going to skip ahead a little. So you could even imagine that once upon a time there were all these Dyson spheres all across the galaxy by this wave of galactic settlement, and that they've just all destroyed themselves. But what happened to that dust? Well, it's, as I said, a lot of it may have been blown out into the interstellar medium. And, well, what happens when it's in the interstellar medium? Well, the interstellar medium becomes this sort of reservoir. And the solar system is moving in that reservoir. So I think that's sort of what happens there. That's sort of going to be one of the things Lewis is going to be talking about in just about right after me. So I'll leave it there. Okay, thank you.